guys, you were tasked with last time to find a way to improve our code for this is it prime to determine if something is a prime number or not. And the reason that we want to do something like that is because just watch how long this is a number that's in the millions, right? 1,141,731. And I want you to see how long it takes for Octave to determine if this is prime or not. So I've got Octave right here. I've got our timer right here. I'm going to hit enter on Octave and start our timer. And I'll pause it because this is not going to be quick. Alright, there it is. So roughly right at 48.5 seconds that it took to determine if that number is prime. Okay, so we want to improve that. We don't want it to take that long for us to get our answer if it's prime or not. So if you look at our code and what it's done, we started with a number. We'll give it a number, and for 1 all the way up to that number, it's dividing by every whole number up to there. So here's a way to improve it. It's not the way, but it's a way. So take a number like 81. You know, what things divide 81? So if you remember from, down in the grades, these are like factor trees. You make this number and then you put a T underneath it, and you can put like 1 and 81. Right? 2 doesn't divide it because it's not an even number, but 3 divides it. Right? 3 will go into 81 27 times. Right? Is that right? 3 goes into that. 3 goes into that 2 times. Remainder of 2. Yeah. And then 4 doesn't go into it. 5 doesn't go into it. 6 doesn't go into it. 7 doesn't. 8 doesn't. 9 does. And 9 is a factor, and so is 9. So if I did, is it prime, and then put in 81, it would say it's not. But one of the things that happen in the background is the vector that determines how many whole numbers, or how many clean divisions there are. It would have 6 in there, and so that S would equal 6. But notice, factors always for numbers come in pairs, right? With the exception of a number in itself, the way we're doing it. But what is 9? When it's in itself, if a number factors a number and the other factor is itself, if it divides it and the quotient is the same number you divided by, then that's a perfect square. And these factor trees, they always start off with 1 and build their way to a number, but then they always come back up with the exact same number of factors. So by that, what I mean is, if you give me something like that, it's not a perfect square, like 24. All right. The factors of 24 are 1 with 24, 2 with 12, 3 with 8, 4 with 6, and then 5 isn't a factor, but the next number is 6, and we've already included it on the way back up here, with the other numbers. So the thing is, what we've been doing is going all the way down and then all the way back up. We've been circling through here looking for all the factors. But because they always come in pairs, we don't need to do the right-hand side. We can just do the left-hand side. And then what would our stopping criteria be? What would we stop with? We could stop with, and in this case, there isn't a perfect square, but the closest thing to the perfect square. So the square root of 24, let me bring up a calculator. The square root of 24 is 4.8, all that stuff. So if I check 4 and it doesn't work, and then, if this had been 25, the square root would have been 5, and I would have stopped at 5. But what I'm going to do is I'm going to take the square root and then round that down with something called the floor function. The floor of, if I did 5.32, the floor is 5. Okay? If I did the floor of 5, if it was a perfect square, it would give me 5. So what I'm going to do to modify this code, and what I hope that you guys come up with on your ideas, is the first thing we're going to do is we're going to give a new number. I'm going to call it R, and I'm going to say R is the floor of the square root of n. So the floor of the square root of n. So if we give it n, it's immediately going to take the square root, and then it's going to round that down to the nearest whole number below it. All right, if it's a perfect square, then it won't round it down. It'll just be that perfect square. And now instead of going from 1 to n, I'm going to go from 1 to r. And we're still going to do the same thing. We're going to divide n by I, right? But it's stopping at the square root, or the floor of the square root, the closest whole number to the square root below it. So it's going to divide those, but it's just now we're working, down the now we're working just down the left-hand side of these factor trees. We're just working down this side. All right. The square root of 14 is something between 3 and 4, so this thing would stop at 3. Okay, so that's the idea. It doesn't need to check any of these other numbers. If it has a factor over here, it's going to have a factor pair with it here. Okay, now these are the numbers that would be if it was a prime number, right? There'd be a 1 here and a 17 here. The square root of 17 is a little bit bigger than 4, so this would go 1, 2, 3, and 4. It would check all of those, right? But it's not going to check 5, 6, 7, 8, 9, 10, all the way up to 17. It's going to check substantially less numbers, and it's going to see that this is its only factor, right, of the ones that it checks. And now instead of the s, if s equals 2, now we're going to change that to s equals 1. And that's going to be our criteria for if it is prime or not. All right, so everything else is going to stay the same. It's just now all we need to have is one factor, and now we can do these problems much quicker, right? So now, is it prime? That really big number, I can hit enter, and it checked it immediately, because what's the square root of 11411731? It's 1068. So now we're back to doing things like this. This problem that we did 1 all the way through, this was before we modified it. It did it very quickly. Well, now it can do a number that big in the same amount of time it did a number that size. So it can do a number in the millions in the same amount of time that before we did it in a number in the thousands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. It still takes a little bit of time because that's such a big number. Now we're talking, that's 100,000, that's million, that's a billion. But it did a number in a billion way less than we did a number in the millions. It did in substantially less time. So anyway, that's our new code. That's our modification. If you came up with something else, let me know. But this is what I was hoping that you would see. Just the way that factors are always paired, we can split this down not in half. We're not cutting the number steps in half. We're cutting it down by a factor of the square root of the number.